Welcome into our final video on Chapter 9, Electrochemistry. In this video, we will look at some applications of electrochemical cells, including batteries, corrosion, and electrolysis. One major application of electrochemistry is batteries. We've been talking about voltaic cells, galvanic cells, as a way to separate redox reactions into two separate but connected half reactions. Well, that's exactly what happens inside of batteries. Here's a picture that we might associate with our typical battery. We have a positive terminal and a negative terminal. Inside that battery, we have our two electrodes. They're separate from each other. Here we're using some absorbent as a separator, keeping our two half reactions apart from each other. And we can look at our individual half reactions. Here we have a zinc anode, which implies that our zinc is being oxidized, probably turning into zinc 2+. At our cathode, we have a graphite rod. Graphite here is going to be inert and conductive, and the species that is actually being reduced will be this manganese 4 oxide. When we set up our battery like this, our anode will lose electrons. Those will be transferred across our battery to our cathode, where those electrons get consumed. We're producing some current and we're applying some voltage. There's a voltage difference between our anode and our cathode. That voltage difference is what you see labeled on your batteries, right? We might have a 9-volt battery, might have a 2-volt battery. Depending on the specific half reactions involved, that will dictate our cell potential, that will dictate the voltage of our battery. We can also do some clever engineering with our batteries. If we have multiple half reactions in series or in parallel, we can do some engineering to increase the output of our current or increase the output of our voltage, depending on what we want. A second application of electrochemistry is corrosion, is rusting. We know that when metals are out in the environment exposed to air and moisture, a lot of them tend to rust. Typically, iron rusts very easily. If you leave your bike out in the elements for too long, it'll start to get all rusted and corroded. Here in this picture, we have a big ship in the ocean also starting to rust away. This rusting process occurs because the metal is being oxidized by oxygen. If we're looking at our standard reduction potentials, oxygen reducing to water has a reduction potential of 1.23 volts. That means that this is a reduction reaction that likes to happen. Oxygen is relatively easy to reduce, which means that other metals present might be oxidized. Our intuition is that when we are building redox reactions, if we have a reduction potential that is very large, this reaction is very likely. And at the other half reaction for our oxidation, a large oxidation potential also is likely to happen. If we're only using our reduction potentials, that means the reaction that is occurring at the anode, our oxidation, will need to have a very negative reduction potential in order to occur readily. Let's pull up our chart and look at this. Here is a list of some standard reduction potentials. Things that are high on this list have large reduction potentials. If we look at the very, very top, fluorine gas reducing to fluoride has a reduction potential of 2.87 volts. That means that this reduction is really easy to have happen. It really likes to happen. If we build a redox reaction using that reduction, and any oxidation underneath it will end up with a positive cell potential and a spontaneous reaction. Let's think about an example. If we have fluorine gas reacting with silver metal, well, fluorine can try to be reduced and silver can try to be oxidized. Looking at our standard cell potentials, we can calculate this taking 2.87 minus 8.0. For fluorine reacting with silver, we would have a standard cell potential of about 2.07 volts. This is positive and this is spontaneous. If this pattern is going to be true, when we have a reduction reaction that's high on our chart, it's going to be more likely to be spontaneous. Fluorine gas can oxidize anything underneath it. Getting back to our example of corrosion, oxygen has this high reduction potential, and most metals underneath it are going to be oxidized by oxygen out in the world. Here we can highlight iron. Iron rusts especially easily. It has a negative 0.45 volt reduction potential. At standard conditions, this reaction is certainly going to be spontaneous. And also in real life conditions, this reaction is going to occur, for example, for this iron ship just sitting out in the ocean. If we've made all this effort of building this whole ship, we'd like it not to just rust away. So one thing we can do is staple some zinc onto our boat. These zinc anodes are going to be oxidized away before our iron can, because zinc has a negative 0.76 volt reduction potential. Zinc is even easier to oxidize than iron, which means zinc will be oxidized before iron gets to be oxidized. If we staple these chunks of zinc onto our boat, they will get oxidized, they will start to corrode away. But if that zinc is corroding away, our hull of our ship is not, and our ship will remain floating for much longer, remain intact. The key here for our reduction potentials, we can use those to infer when reactions are spontaneous. And if we have a few options for spontaneous reactions, the one that actually occurs first will have the largest cell potential. One last application of electrochemistry, we can look at electrolysis. Up until now, we've been thinking about voltaic cells, which have a spontaneous reaction occur because we have positive cell potentials. We can also do the opposite. We can force a non-spontaneous reaction to run by applying a power source. This is our picture on the right. If we have a large battery hooked up to our cell, we can force the reaction to run the way that it does not want to go. In order to do that, we need to have a voltage source with a voltage larger than our magnitude of our cell potential. We can relate this back to our water analogy from previous videos. Water will spontaneously flow downhill, right, from high altitude to low altitude. If you want water to go the other way, you can tip the scales. You can take your low altitude, maybe water jug, and lift it up higher than our originally higher altitude water jug, right? That way you can have our water flow kind of backwards than what you would initially expect. You can put some work into this to tip the scales and make water flow the opposite direction. For our electrochemical cells, we expect electrons to flow from our zinc electrode over to our copper electrode, right? That's the spontaneous direction based on our cell potentials. But if we want this to be forced to go backwards, we can apply a power source, a voltage source, so that Okay, now instead of being at a lower potential, our copper electrode can be lifted up to a high enough potential energy so that the electrons are forced to flow backwards. We hook this up to a battery and we tip the scales. Here's a quick compare and contrast between our voltaic cells and our electrolysis cells. Oxidation is still at the anode, reduction is still at the cathode. But now we need to have a power source in order to force those electrons to flow the opposite direction we'd expect. Here's a practical example. If we have molten salts, we can run an electrolysis cell using these sodium ions and chloride ions, for example. Here is our potential at our anode. It's going to be 1.36 volts. This is the reduction potential for chlorine gas turning into chloride. Here's our reduction potential at the cathode, negative 2.71 volts when we have sodium ions turning into sodium. Sodium ions do not like to be reduced. Chlorine gas does not like to be oxidized. If we combine these together, our cell potential is negative 4.07 volts. This is very non-spontaneous. However, we can force this to run if we hook this up to a voltage source where the voltage in this battery is greater than 4.07. This starts to tip our scales and forces our chlorine ions to oxidize into chlorine gas and forces our sodium to reduce into sodium metal. If you've ever wondered how these group 1 metals can be isolated and purified since they're so reactive, well, this is how you do it. You need a big old voltage source to force those reactions to occur. In real life situations, things can be a little bit more complicated if we have mixtures where there are multiple oxidations possible and multiple reductions possible. The easiest reaction to occur is the one that will occur. Our redox reaction with the largest cell potential is the one that will occur first. This can be useful. We can do this as a purification method. If we want to isolate just one metal out of our mixture, well, the metal that will reduce first is the one with the largest reduction potential. Here we can look at an example. If we have potassium iodide and sodium bromide, what products can we make? We can start by looking up our reduction potentials for all these possible ions. And then we can try to construct a redox reaction with the most positive cell potential possible. Our cell potential is the cathode minus the anode. And what we have is our metal ions being reduced and our halogen ions being oxidized. That means we need to choose between potassium and sodium for our starting value at the cathode. We get to choose between iodide and bromide at our anode. To make the most positive cell potential, we're going to have to choose sodium and we're going to have to choose iodide. So the question says, what products are obtained? We'll make some sodium metal at our cathode. We'll make some iodine at our anode. The previous example was looking at molten salts. The reason that we use molten salts instead of dissolved salts is because water can be oxidized and reduced. And as we just saw, if there are multiple things that can be oxidized and reduced, you might not always get the half reaction that you want to occur in these aqueous mixtures. For example, when we have water, the oxidation reaction is water turning into oxygen 4 electrons and some 4 hydrogen pluses. This has a reduction potential of 0.82 volts, which is perhaps easier to oxidize than some of the other things that we were looking at, like our halogens. Water can also be reduced into hydrogen and some hydroxide. Here, the reduction potential is negative 0.41 volts. Again, easier to reduce water than it might be to reduce some of these group 1 or group 2 metals. One last example here, if we have an aqueous mixture of nickel 2 chloride, can we predict our products of this electrolysis cell? Nickel can be reduced, but actually water can also be reduced. We need to be careful. Chloride can be oxidized, but as we just saw, oxygen can also be oxidized. And so again, we need to be careful. Our cell potential is going to be based on our cathode minus our anode. For our cathode, we have two choices. To build our most positive cell potential, we're going to have to reduce our nickel. At our anode, again, we have two choices. We're subtracting this potential, so we want to choose the smallest value. In this case, water is going to be easier to oxidize than our chloride ions. Put another way, with these possible half reactions, the most positive cell potential we can build is negative 1.08 volts based on our nickel ions being reduced and our water being oxidized. To summarize here, whenever we have a mixture, we need to be careful. The non-spontaneous reaction we force to occur is going to be the easiest one, the one with the largest cell potential. One final note for electrolysis, when we are forcing non-spontaneous reactions to run, we need to apply a voltage source larger than our standard cell potential so that we have our standard cell potential and our power source add up to some positive number. In practice, we actually need to go a little bit overboard. We need to do even more of that than we'd expect. We call this an overvoltage. In order to force non-spontaneous reactions to run, we need to go over the expected voltage, at least by a little bit. All right, that will do it for our video here on Chapter 9, Electrochemistry. Please let me know if you have any questions. Otherwise, look forward to seeing you in our next chapter. Thanks.